All right, so our question today is, as opposed to last time, now you shoot a laser beam through two tiny vertical slits that are side by side onto a wall. What do you think you'll see on the wall? So that was the question posed today. And now, for those of you who are watching at home, I'm just going to show you what our results were from this experiment today. So, what we did is we shined a laser beam through this. It's called a diffraction grating. On the top, we've got slits that are very close together. On the bottom, we've got slits that are far apart. And so I'm going to shine the laser through those in order, and we're going to see, keep it down a little bit, guys. We're going to see exactly what changes on the whiteboard as we do this. So, I have no idea if my voice can be heard from back here, but we're starting with the slits that are close together. Slits that are close together, and you can see we've got 3 dots relatively spread out there. Now, as we go to slits that are closer together, that are further apart, the dots get closer together. Further, another. All right, so hopefully what you saw on the whiteboard is that when I began with the slits that were close together, the dots were pretty spread out. And as I went down the line and these slits got more spread out, the dots got closer together until you got to the very end when it looked like it was just a clump of a mess. But if you looked real close, you could tell the difference between the individual dots. So the question is, what does this all mean and why is it important? And how does it show us how light behaves as a wave? So let's take a look. I would like to call your attention to Exhibit 1, our Light as a Wave worksheet. Remember, from this worksheet, folks, number 4, when you drew these maximum lines here, these 2 wave sources were relatively far apart there. So then the question is, what happened when we took these 2 wave sources and we brought them closer together? Well, we can find out because that's what we did for number 6. In number 6, those 2 sources were moved closer together, and the maximum lines spread out. They were much further apart. Any guesses on what that has to do with what you guys just did today?
Physics.
Yeah.
The smaller the slit.
What's that? Oh, we're going to get to that. That's coming up next. In terms of the red one, though, Keegan.
This is just like, you have to deal with like inverse relationships.
That's true.
Yes.
So there's an inverse relationship both on the maximum lines on this worksheet and the wave sources. Because as we brought these wave sources closer together, the maximum lines got more and more spread out. And when we shined a laser through slits that were close together, the dots were more spread out. As the slits were further apart, the dots got closer together. It's an inverse relationship with this, and it's an inverse relationship with this. I've got one more thing that we want to talk about with this, though. Remember with the green laser and the red laser? The red laser was the bigger wavelength. And was that more or less spread out than the green one when you saw it?
More.
The red one was more spread out. It was further apart, the dots were. So let's take a look at number 7. Hopefully.
So that would be compared to the red one.
Yeah. So here, we took the same wave sources from number 4. We kept them as the same distance as number 4, but all we did is we made the wavelengths bigger. If you make the wavelengths bigger, what happens to the maximum lines?
They get spread out.
Yeah, they get more spread out. That's exactly what happened when we shined the longer wavelength red laser through the diffraction grating. It got more spread out. And so, again, these are longer wavelengths. They correspond to maximum lines that are more spread out, just like the red long wavelength laser corresponds to dots that are more spread out. So what this all means, folks, and the reason that Worksheet 4 is such an important worksheet, is this shows us exactly how light behaves like a wave. Number 1, when you send it through one narrow slit, it spreads out. Number 2, from this worksheet, when you send a beam of light through slits that are close together, you get dots that are spread out, just like maximum lines on worksheet number 4. And when you send a long wavelength red laser through these, you get dots that are more spread out than the green, which are smaller wavelength, in the same way that the long wavelength maximum lines are more spread out on this worksheet. And so essentially, what are you seeing when you see those dots?
Wave. It's spreading. Wavelength.
What you're seeing is you're seeing the maximum lines of that laser beam. And I can show you even more about these maximum lines with the laser. And I feel really bad for the folks at home on this one, because you're not really going to be able to see this. But you can actually make 3-dimensional maximum lines. And the best way to see 3-dimensional maximum lines is with the aid of a fog machine. So who wants to see some 3-dimensional maximum lines?
Me.
Good. Okay.
I really want to see
I'm
it.
going to have to stop the recording now. Sorry.
Sorry, guys. You're an idiot.